and she will be talking about probing the atmosphere for red supergiant stars with a Hubble telescope.
So why would I want to bother probing the atmosphere of a supergiant star? What is a supergiant star? How many of you have had ever any astronomy classes that are here in the audience? Very few. How many have had physics classes? Most of you. I'll ease off a little bit on the physics background, but I still want to make sure that when I show plots of stellar spectra, you know what I'm trying to show. Well, why I want to bother mapping the atmosphere of this supergiant star, I want to explain a little bit about the future of our sun to tell you why I want to do this. Right now our sun is shining because deep in its interior, it's a nuclear fusion reactor. It's converting hydrogen to helium. And the total mass of the helium nucleus is a little bit less than the mass of the 4 hydrogen protons that went into it. And by Einstein's E equals mc squared, a little bit of mass goes a long way and generates a lot of energy. So for a total of 10 billion years, our sun will be fusing this hydrogen to helium in its core. Now gravity is always trying to pull a star in upon itself. But when a star does have the fusion going on in its core, there is additional pressure generated from the energy in the fusion that pushes back against the inward pull of gravity and allows the star to become stable. But 5.5 billion years from now, when our sun runs out of hydrogen in its interior, the core will no longer be able to support itself against the gravity when the fusion is done. There will still be a ring of fusion going around outside the core, and it turns out from a balance of about 5 different differential equations that astronomers crunch through on computers, that the net result for the surface of that star is that it will expand and cool. And our sun will, during this phase of its lifetime, expand enough to eventually, it's not clear yet whether it will completely engulf the Earth or whether it will just bake us into a charred cinder, whether it will vaporize us and incorporate us into the sun. But we got more pressing worries like getting home in a blizzard tonight rather than 5.5 billion years from now having the sun swallow us up. But then its core will contract down enough and get hotter enough for helium to fuse on the heavier elements of carbon and oxygen. And our sun is not massive enough for its core to compress down and generate heavier elements after that. And when the sun's core is done making the carbon to oxygen, some of its outer layers will be blown off in a phenomenon we call a planetary nebula. And will leave behind a core which is called a white dwarf star. Gravity again is trying to pull the white dwarf, the remaining core, down in upon itself. But when you cram electrons in too tightly, they set up an additional pressure to resist that gravity. And as long as the remnant of the star that's left over after this planetary nebula phase is less than 1.4 times the mass of our sun, the pressure set up by these called degenerate electrons can stop it from contracting down any further, and we will have our sun will be what's called a white dwarf star. And it will sit there and gradually radiate away the heat that's still contained in the core. Over billions of years, it will cool down and eventually become a red dwarf, and then what we will call a black dwarf. Now, more massive stars than our sun can build up to heavier elements in their cores, and they actually, at the end of their lifetimes, turn into supernovas. But the stars that are big enough to do that, their cores are bigger, and their cores are too large to stop at being white dwarfs. If it's more than 1.4 solar masses, the electrons cannot hold themselves against gravity, and gravity pushes them closer together, but then they can no longer be electrons, so they combine with protons and they make neutrons. And you can cram neutrons a lot more tightly down. If you had 1.4 times the mass of our sun in a white dwarf, that thing would have about the diameter of the Earth. If you had 1.4 solar masses of neutrons, the thing would be smaller than the island of Manhattan. And so the neutron degeneracy can hold that contracting core back only up till about 3 solar masses worth. And if something is more than 3 solar masses worth, when it's the end of the line core of the star, as far as we know, there's nothing to stop it from collapsing all the way down to make a black hole. So the prediction is that If the remnant after the star's normal lifetime is less than 1.4 solar masses, you get a white dwarf. Between 1.4 and 3 solar masses, you get a neutron star, and above 3 solar masses, you would get a white dwarf. Yet we have observed in stellar clusters, we've observed white dwarfs that we know must have come from progenitor stars that were more massive than 8 solar masses. And to explain why we know that would be half of a class in Astronomy 101. You look like you want to raise your hand and ask a question.
Just say that only 3 solar masses you get a white dwarf.
If you get less than 1.4 solar masses, it's a white dwarf. Between 1.4 and 3 neutron star, and greater than 3, it's the black hole. Did I mess up and say white dwarf?
I think maybe.
Yeah.
Okay. Thanks for catching me. So anyway, the idea is we do see a white dwarf star that had to have come from an object that started out more than 8 solar masses. So these stars are losing matter along the way. And in the red giant and red supergiant phase, there is a mass loss that we can observe, that they're shedding their outer layers. Something like 1/1,000,000th of a solar mass per year. And if you have a large star that has that big of a mass loss rate, it can shed quite a bit of, it's like, join Weight Watchers now, avoid becoming a black hole. And so I'm kind of watching the diet process on these stars to try to measure how fast they're getting rid of this mass. So that's what I'm trying to do here, is map out the part of the star that is undergoing this mass loss, because I got interested, started working on this field in the mid-70s, and I was like, well, we can begin to measure how fast the mass is being lost, but we don't know what's causing it. Now, it's all these years later, 30 years later, it's, well, we can continue measuring how fast the mass loss is going, but we still don't know what's driving the mass loss. So I'm trying to get more detail on the process of the mass loss so that we can hopefully use that to teach us about why. What's driving the diet? Is it low fat and high fiber, or is it Atkins? Anyway, in order to show you how I'm studying the atmosphere of this star that's losing the matter, I need to give you some background in spectroscopy. Some of you will know this stuff, and some of you may not know it. It's really worth my while to spend a few minutes making sure that you can follow all these plots of stellar spectra that I'll be showing later in the talk. And if you shine light through and it's showing in this intro level textbook view graph, if you shine it through a prism or a diffraction grating, and you spread the light out into all the colors of the spectrum, you're spreading the light out, separating the long wavelength light from the short wavelength light. And the red end of the spectrum is the longest wavelength, but when you treat light as a particle instead of a wave, then the individual particles of light at the red end actually have less energy. The short wavelength blue and purple light have the most energy per photon. If you have if I were the one writing this textbook, I would change this annotation, but it's not the best illustration, so I'll leave it anyway. This should just be dense is more important than hot, because anything that is dense enough will generate what we call a continuous spectrum, and all the colors of light are present. Now, the shape of this curve depends on how hot the star is. If for a hotter star, you will have this, what we call the peak wavelength here, shifted to shorter and shorter wavelengths. Now, if you send light that has all the colors, came from this dense source, like the filament of the light bulb, if you send it through a cloud of tenuous gas, where the atoms are far more separated from each other instead of tightly packed as they are in the solid, then you get these line spectra. And it depends on which angle you're looking at the cloud of gas, whether you see dark lines in absorption or whether you see bright lines in emission. I'm going to put another view graph up for a minute here and then come back to this one again one more time. But the reason that we get lines is that electrons are only permitted to be in certain orbitals around the nuclei. You've probably heard a lot about this in high school class, that how the periodic table is built up by you get 2 electrons in the inner shell and you get 8 electrons in the next shell. the different shells of these different energy levels. And the farther away from the nucleus of the atom that the electron is, the more energy it has relative to the nucleus. And this is the simplest atom of all, the hydrogen atom, with its simple single energy levels here. And for example, if you had an electron in level 2, and if it drops down to level 1, it has to get rid of that extra energy that it has, and it does so by giving off a particle of light that contains that energy. And in the case of dropping from level 2 to level 1 in hydrogen, that's actually a high enough energy photon that it's an ultraviolet wavelength that we can't detect from the ground. From level 3 down to level 2 will give you a red photon coming off. However, if you shine a continuous spectrum with all the colors through a bunch of these atoms, and you have an electron sitting in level 2, it can take red photons that have just the right amount of energy to jump it up to level 3. And so those photons will be missing. So let me put this is one of the ones I want to come back to later. Nope. There. So here you've got all the colors of light that have been emitted by this continuous source passing through the tenuous cloud of gas, and the colors that are missing here are because photons of this light were taken by atoms within this cloud, and those electrons jumped up to upper levels. And that's, each individual atom has its own pattern of energy levels, and therefore its own pattern of photons that it can absorb. And you can look at the lines and tell what chemical elements are present, and you can look at the shapes and strength of the lines to tell how much of each chemical element is present. And that's if you're looking through the cloud of gas to the hot light source, the dense light source. But if you're looking at an angle through the cloud where you don't see the continuous spectrum itself, you don't have the continuous background. All you have is what we call an emission spectrum, and you have bright lines instead of dark lines. And that's because when the light from the continuous source goes through and the electrons absorb the photons and jump up to upper levels, they don't stay there forever. Typically after 10 to the minus 8 seconds or so, they will spontaneously drop down, but they got to get rid of that extra energy, and it comes off as photons. But they don't necessarily come off in the direction the initial light came in. They come off in all the different directions. So if you're looking at the cloud from this direction, you won't see the continuous source, but you will see the emission lines that arise from the electrons that are up in those upper levels dropping down. And the photons that are given off from an electron dropping from one level down are the same wavelength as the ones that are absorbed to go from that same transition upwards. So there's a reason why you have these two lines marked here and also here. And the one other thing I want to make sure that you see from this particular view graph is that the way that these spectra, this is what you would see if you put a diffraction grating up to, or a prism or diffraction grating up to light shining through a slit. But this is how you would plot it on a graph. You would plot wavelength increasing this direction and then how much energy came off at that wavelength. So you'll see a number of plots through the rest of this talk where there will be the continuous part here, and then there will be dips when there's an absorption line, or there will be places where it rises up when there's emission. So, and then finally, one last piece of spectroscopy background. Why do I want, or why do I get to use the Hubble Space Telescope to do this? Now, most of you, when you think of the Hubble Space Telescope, you'll think of all these really pretty pictures and fine detail imaging that you can get when you're up above the atmosphere. Well, actually, I should wait a second on this. I should show you my star system first and then show you why I need Hubble to observe it. This is, the IUE was an ultraviolet satellite that was, well, this is about, I think it lasted one more year beyond this. It was an 18-inch telescope that observed at ultraviolet wavelengths. And this is my star system. Okay, this is a supergiant star. Okay, now this is the orbit of its companion. It's a binary system. There is a big, very large, what we call supergiant star around which a smaller star is orbiting. This particular supergiant, it's like 20 solar masses worth, so it's much bigger than our sun, and so when it's in its red giant phase, it expands out to a lot larger. And this thing would go beyond the orbit of Jupiter and partly to Saturn if we put it in the place in our solar system where the sun is. So our orbit would be down in here somewhere, in the size of this thing. And it has this smaller in size, and the dot here is actually relative to the size of this. The dots are too big to display the size of the companion star. Now this one is a red supergiant. It's a cool star, and this one is a hotter star. And my whole way in which we map out the atmosphere is when the hot star, we're lucky that the orbit is lined up such that you've got the great big star here and the little one. So I guess I'll use the tip of my index finger here to be the little star, and imagine the big one here. And so as the little star comes out of eclipse from behind the big one, it provides a continuous source that shines through the tenuous cloud of the atmosphere of the big star. And as this thing moves in its orbit, it's going to shine through successively higher layers of the M supergiant atmosphere. And so you can study the structure of this expanding wind as this hot star moves behind it as it comes out of eclipse. Now, why I want to go into the ultraviolet to make those observations, right? This star is much bigger, and the amount of energy that is put out by the star is proportional to its surface area. And so the larger star is going to be giving off more energy and be brighter. However, there's one other effect that tells how much energy is being put out by a star, and that is its surface temperature. And so this view graph here represents the behavior of dense spectra, objects that are hot enough, objects that are dense enough to give off continuous spectra. And the hotter they are, the shorter the wavelength their peak is, plus they give off more energy at all wavelengths. And if you integrate under this curve, the total amount of energy given off per square meter of a star's surface is proportional to the 4th power of the temperature. Now that small star doesn't have a lot of surface area, but it's hotter. So if you try to observe it at long wavelengths, the red star, it's a cooler star. Its temperature is such that its continuous energy distribution peaks in the infrared. In visible light, we'll see more red from that star than we will violet, and our eyes will call that a reddish star. A star like our sun, its temperature puts its peak wavelength right in the middle of the visible light range, and all the colors added up, we see a yellowish star. For the hotter stars, with their peaks out in the ultraviolet, then we see more violet and less red, and we see a bluish star. But it's also, every square centimeter of it is brighter than every square centimeter of the red star. By the way, the art department has been lying to you all along. The hottest stars are blue and the cool stars are red. Now that's, granted, we aren't used to seeing blue hot things in everyday life. We're used to seeing blue icy glaciers and red hot things, but that's just because we don't experience these sorts of temperatures on a daily basis. So why did I get to use the Hubble and the IUE? Why did I want to do that instead of going and observing from the ground? Is because the small star that I'm using as my probe is way brighter in the ultraviolet than the big cool star. So you don't have to worry as much about the light from the cool star messing up your observations. But as you'll see, we still have to pay attention to it and worry about it. So that's why I go into the ultraviolet to do this, and why I use the Hubble Space Telescope. So anyway, now I went to graduate school at the University of Hawaii. Yeah, it was Hawaii. And I went to work there with my advisor was working on the diet process from M supergiants, but not in a binary system like this. And it was actually the first star that was discovered to have this mass loss was Betelgeuse, one of the red corner star in Orion, back in the 1930s. When they took spectra of it, they would see absorption line profiles. There's a continuum, and then you have these various absorption lines. And most absorption lines in a star will have it. That's supposed to be a nice symmetric line profile. Be another symmetric line profile. And then there were a few lines in this star system that had these funny dips at the bottoms of the line profile. There was extra absorption occurring here that was off-center from the line center. And what makes these be off-center is the Doppler shift. Right? You heard when a siren comes at you, you hear, "Meow!" If something's coming toward you emitting waves, the waves get compressed up and you observe a shorter wavelength. And then as the siren moves by, and the waves are emitted from slightly farther away every time, then the wavelengths appear to stretch out. And so what this is an additional little absorption line at a shorter wavelength. And that's because as we look toward the star, we're looking through this expanding atmosphere. And so it's about a 10 kilometer per second typically shift that these little blue shifted, we call them blue shifted cores, because they're shifted toward the short wavelength end of the spectrum. They're showing that this matter is expanding away from the surface of the star at about 10 kilometers per second. So I got into this whole studying the mass loss process from stars by working with an advisor who was taking spectra of stars from the ground and observing these little dips because of the wind. Okay, so the background is now out of the way. So I went from that graduate school thing and my postdoc at Harvard-Smithsonian started in 1977. And I knew about this system, and it has, with the hot star coming in and out of eclipse, it's a 20-year orbital period. And it stays in eclipse for about a year and a half, and then you see atmospheric effects in the eclipse for several months as the hot star comes up and then goes back into eclipse. And so I was getting out of graduate school right around the time of this eclipse of this star system, so I was eager to go to work on it. And I was lucky that where I landed for my postdoc, they, meaning NASA, was just about to launch this IUE satellite, and one of the women there at Harvard-Smithsonian had time on it to observe the eclipse of this star. So I was like, oh boy, I get to get involved in this project, and she said, oh goody, I have a postdoc to do the grunt work. So, now the IUE was launched. We did not manage to observe during total eclipse. This is the line of sight to the Earth. And as we have a whole bunch of observations as the hot star is coming out of the eclipse, we did not get to see it during totality. But the idea was we were hoping that, or what we were expecting to see, I shouldn't say hoping, but expecting to see, is that as the hot star came out, these hot stars don't have a huge number of absorption lines in their spectra generally. And so we expected to see, as the hot star came farther and farther out, that there would be fewer and fewer and weaker absorption lines in the spectra. So this was the first observation we had in which there was not a lot. This is, again, brightness versus wavelength. And this is out in the ultraviolet. This one was before the hot star had completely come out. It was during the partial eclipse phase. And now the hot star is out. You have the hot star continuum. I'll get to these emission lines a little later. And then you have these absorption lines. In this particular region of the spectrum, a lot of these are due to neutral iron. And then as the hot star came farther and farther out of eclipse, these iron lines went away gradually, and then by a few months after eclipse, there's still some stuff going on here by this strong iron 2 line. Iron 2 means singly ionized iron. But a lot of the absorption has gone away, and we expected that we would see, when the star came far out of eclipse, that we would just see a hot star-looking spectrum. Well, we were kind of fooled, because even way out of eclipse, it still remained messy in other regions of the spectrum. Now this view graph here compares BB Ceph, which is my old friend, to another star with another supergiant and another hot star companion, but the wind in this 31 Sig star is not so extensive, so the hot star is not shining through quite so much stuff, and it really does manage to come out and just show you the hot star spectrum. The dotted lines here are this 31 Sig when it's still deep within the early parts of the eclipse, and the solid line is my star when it's way out of the eclipse. It's as far out of the eclipse as it gets. And so the hot star still remains shrouded in all this stuff. And the 31 Sig, the dotted line spectrum, was actually quite a simpler case. And so I went to work on it for quite a while. Now this is all, when this satellite went up here, there had not yet been a whole lot of ultraviolet astronomy done. There had been one previous ultraviolet satellite. And remember how I said that you can get the chemical elements, the abundances of the elements, by seeing which lines are present. And as it turned out, the physicists hadn't really gone to work on trying to predict what lines would be visible in the ultraviolet because the astronomers hadn't really had a chance to do the observations yet. So here was this huge, complicated spectrum, and we really didn't know what chemical elements were giving rise to these lines. So a project I did in the early 80s was to get a hold of the latest physicists' compilations of line data and match it. And I was able to do a really decent job of figuring out nearly every one of these absorption lines in 31 Sig. And it made me confident that I was understanding what was going on. But then there were still these extra lines in BB Ceph that were not seen in 31 Sig. And I at least thought to find an analogy, hunted around for in a lot of stars, through the literature trying to find other sources that might have those lines, these ones in 31 in BB Ceph that were not seen in the comparison object, and then sure enough another object. This is one of the Pleiades. I don't know how many of you know the Pleiades constellation, the little things. It's a little group of stars that are often called the Seven Sisters, which I thought was really appropriate for Mount Holyoke was teaching at Wellesley, to find a dear friend in the Seven Sisters constellation. This is a hot star that's surrounded by a bunch of stuff, and I found a nice friend there. But anyway, there were a couple of other bizarre things that we saw in, well, many other ones, but few that I'll have time to talk about today, that were seen in the data. These are two other regions of the spectrum. Now the solid line is my star, and the dotted lines, well, the dotted lines is the other my star. And it's really strange that in the comparison star, many lines approach zero central intensity, whereas in BB Ceph they don't. The only ones that approach zero central intensity are shown here, and they are the same features that would be expected to show this. Only the lines where the electrons start down in really low energy levels show these dips. And so all these ones that are down below this sort of bottom level here are ones that show those circumstellar dips. And that's what we're seeing in these low lines on the expanding wind. But why don't the other lines go below it? All right, so nearly 20 years passes, and the Hubble Space Telescope gets launched. And one more time with feeling here, we missed totality. So we put into the Hubble Committee, we meaning some other people that I had met up with in the interim, who do modeling of, I had spent many years poring over these spectra, becoming familiar with the line patterns in the spectra. The other group had worked on quantitative calculations of the similar stars. Both of us wanted to use Hubble, we joined forces. And when the principal investigator on the project, wrote the proposal to Hubble, he said, well, first of all, we were denied the time when we tried to measure it on the way in to eclipse. So now we were left with trying to get it on the way out. And so he wrote, this is very timely. We need to do it now. By the next eclipse, 20 more years from now, all of the investigators will have retired. Well, fortunately for us, as it turned out, the person who was the head honcho of the telescope time assignment committee that time around was the same woman with whom I'd worked on the IUE data. And she was interested in this object, so we got the time. So we, for the first time, were able to observe this during total eclipse. Now this is another view of the orbit of this star, seen instead of where I showed you the last one, we were looking down from above on, like we're looking onto the plane of the orbit. But here's what it looks like as you're looking toward the big cool star from Earth and the slanted orbit here of the hot star. And so we timed our observations so that we would get a couple of observations during totality and then a whole lot of closely spaced observations as the hot star is coming out from behind, and then a few more scattered along the way as you get farther out of eclipse. Well, the darn system fooled us and came out of eclipse late. And we got, and we still don't understand why. Now these stars do pulsate. They do not stay the same size, and they may have just been unlucky in that it was especially large when it came out. So we have 9 closely spaced observations that are still in totality. Now, yes, we wanted totality, but we didn't necessarily want all 9 of them. As it turns out, we've learned some neat stuff from that. But anyway, why is Hubble so great compared to the IUE? Remember this ratty IUE data? It was wonderful at the time, but this is that same region of the spectrum observed with the Hubble. Same exact region. This is an early observation when these lines were strong, and this is a later observation when they're weaker. And if you see these little bumpy things here, here, and here, those things are actually real. They reappear in many, many, many of the lines. And then in the next observation down, there's also little things that reappear in many, many lines. And so the equivalent Hubble graph to this one this ratty IUE data, and ignore the stuff at the bottom because I'm going to come to that next. But, and this is the strong, strong line after it just comes out of eclipse, and then it gets weaker and weaker and weaker and eventually goes away. So, now we haven't done anything quantitative yet on those types of lines, on how they disappear. But there is something quantitative we have gotten to so far. I mean, we will eventually. I got till retirement. The thing will come out of eclipse. We'll go into eclipse next time, right around the time I retire. But as a line, absorption line has more and more stuff doing the absorbing. The line gets stronger, stronger, and eventually these big, broad absorption wings start to come in as the line gets very, very strong. And calculations can tell you how much stuff is between you and the continuous source by how broad these line wings are. And so my colleagues who do the calculations have done that, and this is going to be a bunch of multicolored spectra that what I want you to look at here is this broad wing getting smaller and smaller. This broad wing here getting smaller and smaller, eventually being gone. The strongest line in the spectrum is hydrogen. As it goes, this is 1/2 of the line profile. This is it's way all absorbed, all the heck is gone, and then here's what it would look like coming out. There's all sorts of other absorption. But gradually you can see this line wing getting smaller and smaller and smaller as the thing comes out. So we have begun to do the quantitative part of analyzing this, and we have numbers that show as and my colleague has not yet turned this into distance above the height of the cool star yet, because we're still refining the orbit to know how big the thing is, but you can definitely see that there's less and less and less stuff as the hot star is moving out. All right, where have I been spending most of my time lately has though been in looking at the spectrum during totality. And remember this view graph here, I like to call this Astronomy 101. When you look through the cloud of gas and see the hot star, you see absorption lines. When you look through the cloud of tenuous gas without seeing, in other words, when the continuous spectrum is blocked, when it's behind the cool star, you're seeing a situation like this. You've got the cool star with its big extended atmosphere, and when you're looking this direction at it, you're seeing the emission that comes from this because the continuous spectrum is blocked behind the star. So I'm going to put up one of the regions of the spectrum where we are. Remember that there were parts of the spectrum where it never seemed to come very far out of eclipse? The top graph here is absorption features that are seen when the two stars are well out of eclipse. And the bottom one is totality. And everywhere you see, well, not everywhere, but most of the places where you see absorption well out of eclipse, during totality you see emission lines. Good old Astronomy 101. Now the one place where the absorption stays in absorption is these few places here where you have those little circumstellar lines, because that is absorption farther out in that big wind. So what I've been doing for the last several years working on this project myself is trying to identify the various lines in the spectrum, again, like I did with 31 Cygni, but with this richer spectrum. The next two view graphs I'm going to slap up here show you the whole spectrum we have observed. We observed it over about roughly 2,000 angstroms worth of wavelength. Here is half of the spectrum. Okay, there's at really short wavelengths, it's an absorption-dominated spectrum, but the majority of the spectrum is just emission line after emission line after emission line after emission line. Bazillions of them, well, a little more than 2,000. Not bazillions. So this is the other, this, from 2150 angstroms to 3150. So I have been working on identifying the features. There's a little more updated database of the particular lines that appear in the spectra of, lines that appear in the spectra of stars. Lines that are predicted by physicists. They study the different energy levels of ionized iron, neutral iron, of ionized chromium, all the different elements, and then they compile a list of predicted wavelengths for the lines that should be in absorption or emission, depending on how you look at it. And then they also can predict how strong a particular transition is. How likely is it, if the photon of the right wavelength comes by, will the electron grab it and jump up to the higher level or not? So some of the lines are more intrinsically strong than others, and the databases show it. So, and that's the way I did the stuff I was doing on 31 Cygni. I would look at from the lowest possible line energy levels, see how far down in line strength I would go and still have the lines be present. And you'd move up in a little higher and lower energy level and see how strong the lines you had. And that worked really well for identifying the absorption lines. So that was my first pass at trying to identify and figure out what elements were producing the emission lines during totality here in BD-Ceph. So here is one little section of the plot. And this is out really near that same region of the spectrum that I showed how it comes out of eclipse nicely. In totality, that area still has a bunch of emission lines, and one particularly strong one, that's the emission line you saw in that radial IUV data. That's still, the emission there is so strong that it still stays present even when the hot star is out of eclipse. But and it did a really good job here. I would do this looking at the lower energy level of the line and then trying to see how many, for a given lower energy level, I'd go down in line strength until I didn't see more lines. It did a really good job of identifying the emission features in this region of the spectrum. But what happened to me when I went out to shorter wavelengths, which means higher energies, that same procedure gave me this. There were lines that were selected from the database because their lower energy level was present, but in other parts of the spectrum. But lots and lots of line predictions where the selecting a line based on the lower energy level didn't turn up a feature in the spectrum. And so what I realized eventually was going on was that as you go, what's happening here, the electrons they absorb the photons and they jump up to the upper energy levels. And then they sit there in the upper energy level. But they don't necessarily drop back down to the same place they came from. Remember the nice little simple hydrogen line diagram with just a few energy levels? Well, here is a similar energy level for iron. You've got lots and lots of electrons to interact lots and lots of different ways. It's a huge mess. There are literally thousands of iron lines in the spectrum of this star blended all together. This is just an energy, unit of energy called electron volts that's convenient for expressing energy levels. And I see stuff up to that arises from levels about all the way up to about 14 electron volts here in iron. But one of the electrons, if it jumps up to one of these upper levels here, it can go down to all these other levels. So I decided to, instead of looking at the lower energy level to select lines, to change my process around and look through the tables based on the higher energy levels instead, and just see how they fell from there. It was way, way better. Find that last deep breath here. When I do my line IDs based on the upper level instead of the lower level, those spurious ones go away. Because when you're getting to the really short wavelength lines, that means there's a big difference between the high and the low end. And if you do only the low end, you can have a low end. I tried to mess that up. But in any case, if you base your line IDs on the upper level because the emission lines are going to shine out, the electrons are going to drop all the different ways. I ended up with a much better job of identifying this spectrum. This dotted line here is a line that's probably not identified, even though there's a line in the data table there. It's not strong enough to explain how strong that feature is. There are a few dozen lines I consider unidentified out of this 2,000 line spectrum. I'm really encouraged that our ultraviolet line databases agree reasonably well with this rich emission spectrum. And here is my full spectral atlas. That page there, that's how much data I have on this star. And now that we know what lines are there, we can start analyzing quantitatively what they're telling us about the spectrum. So that's how I have spent the time while I've been at Wellesley. It has not been spent on teaching undergraduate astronomy. So I would entertain questions.
You said something varied is by the fourth power of the temperature?
Yeah, the energy. So what's happening, you've got the surface of the star here. Each square meter of the surface of the star is radiating energy. The amount of energy per second per square meter is equal to a constant times the fourth power of the temperature of the star. So if our sun were to double its temperature and stay the same size, it would radiate 16 times as much energy.
Where does the fourth power come from?
The integral under the curve.
Oh.
And the curve had this black body curve. They measured it. This is something I learned that was really interesting. When they started understanding how hot objects, the different radiation emitted by objects of different temperatures, they started studying that by the way people used to determine the temperature inside their pizza ovens or kiln clay ovens, and the hotter the temperature, the yellower, and the cooler the temperature, the red-orange, and as the oven got hotter, so they tried to study the way the oven went, and they observed that there was a shape of how bright it was at what wavelength. And one of the major steps in the development of quantum mechanics, the whole quantum mechanics theory, came about when they realized that the only way that they could explain the observed shape of this curve was by having the energy in the light be quantized. And the t to the fourth comes from the integral under that curve.
Other questions?
Science.
Let's thank Professor about again.
I was supposed to have given you references to read if you wanted to follow up on this stuff, and unfortunately, I'm working with a sophomore student, and I really can't find any good basic references for this. But I suggest that if you're interested in following astronomy and what people are learning, that you read Stein Telescope magazine, because even the professionals do that. They keep up on fields other than their own. And if anybody wants to email me a question or something, I'll just write the email up here. I'd be happy to answer you.